Okay, this is our fourth lab in AGEC 410 Ag Policy. It replaces the Friday class of the 10th week. We are going to look at nutrition models, economic models of nutrition a little bit to try to get a better handle on some of the food policy guidelines and especially that thrifty food model we looked at in lecture. Okay, so we'll be at least partially replicating that approach, and hopefully using this small example you'll get an idea of what's involved in that from sort of the economic analysis side of things. Yeah, so if we'd spent a lot of time on food policy, we would have thought about data that's collected on foods, especially a big topic is always food inflation. Food inflation and how the retail price of food might compare to the farm price of food. So there's all kinds of topics, but we've been mostly focused on nutrition policy. And in the chapter we use, chapter 10 of Wild. I'm not sure. Whatever the author of that book is that we've been using, section 10.3 actually takes us through the steps of what USDA does to come up with a thrifty food plan. And their approach is a little bit different when you read through it, but the idea is to come up with these targets, right, for what percent of calories are going to be fat, saturated fat, some calcium, some iron. If you kept going, you would see other nutrients, protein, carbohydrates, and so forth. And what they do is they have a target food cost, and then they try to think of, then they also have a target on how many servings they think you should, be spreading your consumption out over. And then they move over here and they finally arrive at the official thrifty food plan, how it's built up. And it's the way they do it is to try to minimize the distance from sort of what they get in current food surveys. So what people are normally consuming already, how do you minimize the difference from that? And so that's one approach. We're going to take a slightly different one. So the fundamental economic model for consumption is always utility. Okay, so we did this problem looking at whether you're better off as a consumer, a low-income consumer who qualifies for a SNAP benefit, Supplemental Nutrition Assistance Program, a SNAP benefit, an income increase. And of course we were able to look at that problem and say that for many it wouldn't matter, but for some consumers they may prefer or be better off if they got just a straight income transfer that wasn't limited to food. But we could take that same utility model, a indifference curve that describes the utility map, a budget line that describes spending or allowable spending, and then goods. I think we had food and non-food in that picture, and solve for the best combination of food versus non-food. Well, it turns out we could also apply that same kind of problem, that same sort of problem to food consumption. Okay, and if we assume that many individuals, right, compartmentalize consumption choices. So if you go and look and survey people and try to get them to respond to how they actually break things down and make choices, it turns out that while the theory may say that we consume everything so that the marginal utility per dollar balances out, and we may actually approximate that quite well in our choices over time, when you ask people to describe their pattern of spending or describe how they make choices on purchases, they do tend to sort of break it down into what we might call sub-problems or a sub-problem approach. And so one of the things you do is you sort of have an allocation to food for the family, food for my own eating, whatever. And if you do it that way, then this sub-problem approach, this I'm talking about, becomes you sort of compartmentalize and say, I'm going to allocate this money to food, and then what's the best way to spend this money between food items, and in this case I'm going to reduce it all to food 1 and food 2. And so what we'd have is the same exact look at our problem, except instead of the full income or the full spending of the household or the person, it's now the food budget, the money that got allocated to food. And then instead of the full utility, it's the total utility you can get from food consumption, and you build an indifference curve off of that, so this food utility is constant. Here, these are the combinations that give you the same amount of satisfaction from food consumption. This is the line that tells you combinations that cost the same and getting a higher utility is better, and so this is the optimal solution. And it has that rate of change solution that we want, right? So the price ratio of the foods is equal to their trade-off in marginal utility. But this, even though this approach is fine and it leaves us with something that gets us down to the level of problem we're interested in, we're always interested in reducing a problem functionally to be small enough to look at the sort of nexus of the policy issue, and so this one does that, but it leaves us a problem, and the problem is, what is utility? How do we know what we're talking about? So we could probably break it down even further. If you think about fundamental demand for food, it is not fundamentally that I want the Twinkie or the pretzel or whatever it is that I'm going to eat. It is that we fundamentally demand these for the nutritional content. Okay, and so if we were willing to abstract from utility and say that people have a requirement, right? So it's not so much a satisfaction level, but a requirement to maintain a certain level of nutrition and consumption across a number of nutritional factors, then we can treat it entirely as a nutritional problem and do the economics on the cost accounting side. Okay, and so it also allows us, one, because there's no utility involved, we can do it all as a computational problem and get away from this theory analysis or graphical analysis that will never hold up because we'll never know people's utility. We should say that thinking of food consumption entirely in a nutrition context is probably going to do poorly if I took my pattern of consumption for food and one of yours, and we compared those on a cost setting. We will probably do a bad job of policy analysis, or even just identifying sort of the drivers between the two of us. Why do we differ? Those kind of things. But if you were a policymaker and you were trying to decide on what's the appropriate level of benefit to provide to a low-income family, you might use the nutritional basis. So you might say, we have to come up with an estimate of what it costs to acquire the nutritional components that we think they don't have enough income to cover. Okay, and from there you are probably looking at also providing them a recommendation, which is where the thrifty food model comes from. So first come up with a level of benefit that you think is efficient, right? So how much taxpayer money are we going to spend on this so that we're not wasting as little money as possible? And then second, try to provide some education and guidelines that helps them use this money in the best way possible to meet these sort of minimized or minimum requirements for nutritional components. Another way, if you're a government department trying to allocate funds maybe for a military base on food purchases, this kind of model might provide a guideline, right? So you are feeding in mass, and you have to procure a lot of food items, and you got to prepare meals, and so meeting these nutritional constraints, and maybe some other ones, right? There's always some palatability or sort of enjoyment diversity of food items, those kind of things. So we've talked about that a little bit. School lunch programs, prison, military, anything where the government is sort of in charge of buying food, they have to make an accounting of how they're spending the money, and so it's a role for this kind of model. A second use might be just tracking the cost of food. Okay, so as I said at the very beginning, if we were doing this class, we might be, as food policy all the way through, one of the things we would look at is food inflation and how do they track it. But the cost of food items, just like the cost of many other things, changes over time, and it can be driven by a number of factors. Okay, so the cost of computers, over time has fallen, but the functionality of a computer has gone way up. So many people are using computers now as their, I guess the cord cutters are as their home entertainment sort of resource. Sort of instead of having a TV, a cable bill, and speakers or VCR. You guys are all too young to know what that is. A DVD player. Now it's a computer, and what can I, and an internet connection, and then if I'm going to watch it on the computer screen, or if I'm going to come up with some, other sort of broadcast. And so food is the same way. So people, there are fads, there are trends, there are things people want, there are dishes that become popular or unpopular. And so you'll be picking up a lot of those things. Anytime you're just out there measuring sort of the aggregate cost of food, aggregate food spending, all of those things will influence it. But fundamentally, the public concern, right, the public information, the public economics criteria about food is how much does it cost to nutritionally, to meet the nutrition requirements of the population. And so being able to break down inflation or cost increases in terms of the nutritional content might be an important piece. Okay, and so if we're going to do this is not exactly the thrifty food model approach, but it's has the same origin. Then let's think about a way that we might do this. And so the nutrition demand approach would say, think about nutrient demands, and then what we would do is compare those nutrient demands in total, right? The nutrient demand or nutrient requirement, and then think about the cost of those nutrients in terms of the foods that you're allowed to, or that you might choose between to gain those nutrients. And so I've put together a simple example, a graphical example here. Let's let P prime be the minimum protein that needs to be consumed, K prime minimum calories, and C prime minimum carbohydrates. Okay? And so if we move over here and we have food 1 on the vertical, food 2 on the horizontal, then a point here would say P prime, you have to consume this much food 2 to meet this target level of protein, or this much of food 1 to meet the target. Okay? If you connect those, you get a line that says any combination of food 1 and food 2 described by this line will also exactly meet the protein target. Anything on this side of the line will exceed the protein target, and anything on this side of the black line here would be insufficient. It will not meet our protein target. And then we could move down here and say the same thing for calories. We have a calorie target. This is how much of food 1. This is food 2. The blue line traces the combinations, and you need to be on the right and above to exceed it. Anything on the inside of the blue line will fail to give you enough calories. Same thing finally with carbohydrates. So C prime, C prime. This is the part that has enough carbohydrates. This part does not. And then of course the line is included. The line has exactly the number that we consider to be the target. Okay, so a few things to be of interest here. So the foods are diversified. Food 1 is different than food 2. Food 1 is an expensive way, right? It takes a lot of food 1 to meet the protein target, relatively little of food 2 to meet the protein target. Food 1 is a cheap or a efficient source of calories, of carbohydrates, right? It takes not a lot of food 1, but it takes a lot of food 2 to meet the carbohydrate constraint. So maybe food 2 is tuna, and food 1 is, I don't know what a high carbohydrate food would be. French fries or something maybe. but anyway, this is the interesting part of the problem is that foods are not all made the same, right? They do not all have the same calorie content. And so while food 1 you could rank by going here, it's most costly in terms of how many units of food 1 do I have to consume to get protein from, but it's relatively good at providing carbohydrates compared to calories and protein. Food 2, well, its categorization or its characterization might be it's a good source of protein compared to carbohydrates. We can't say whether it's expensive or cheap because we haven't added cost yet. We don't know. Food 1 could be very cheap food, and so it could end up being cheap way to get protein and everything else. Okay, so a better way to look at this would be, if we say that we have to be to the right of the protein constraint or on it, to the right of the calories constraint or right on it, and to the right of the carbohydrate constraint or right on it, or to these lines, then what we're actually doing is building out this nutrition demand as a frontier. Okay, we simultaneously have to meet all of these requirements, the protein, the calories, and the carbohydrates. It means nothing, right, to say I've consumed enough protein if in fact you've consumed the protein amount right here through this combination and you failed to meet the carbohydrates and calories constraint, the minimum calorie target or the minimum carbohydrate target. So a nice way to do that is to just strip off the extra part of those and make this a true nutrition frontier where we have the part that's contributed by protein, the part that's contributed by calories, and the part that's contributed by carbohydrates. Now we trace this frontier and say any combination of food 2 and food 1 that is on this frontier, on this kinked sort of demand space, would give us exactly enough to meet, would meet our conditions, our targets for protein, calories, and carbohydrates simultaneously. Anything to the right of this kinked frontier would also meet that, and in fact it would produce all of them in excess. Anything to the left or below here, inside of this frontier that's been partitioned off, is what we would call infeasible. So we are not allowed to produce a diet or a combination of foods that doesn't meet the targets. Okay, if we were, right, then the solution to this problem of finding a low-cost diet becomes really simple. You just go down here and spend nothing, and we know that's not allowed. So once you rule out not consuming food, then the only way to do it is to consume enough to meet the targets. It is interesting that each, and you'll understand this a little better as we do the solution in the spreadsheet model. The protein constraint sort of controls this piece of the boundary. The calories constraint or the calories portion or demand controls this, and the carbohydrate target controls this. And then there's a point right here where both calories and carbohydrates simultaneously control the diet, or the low cost, or the target front of the frontier. And then this corner right here, both calories and protein. Okay. And so we have to think about how do we get the best combination now that we have the set of combinations. All these combinations will satisfy our problem of meeting the targets, but our objective is to get the lowest cost way. And so that means we have to do a little bit extra. So the right way to do it would be to start with a cost function. So add a cost measure to the nutrition frontier, and this is what the cost function looks like. So let's let F1 be food 1, F2 be food 2, P1 is the price of food 1, P2 is the price of food 2. Then you could say that the total cost will just be food times price plus food times price. And then if you wanted to rearrange it, because we have this graph that says food 1's a vertical axis item, food 2 is a horizontal axis item, then the way to rearrange that is to solve for an ISO cost line that says F1 on the left-hand side, and then move everything else to the right-hand side. So you end up with the slope being the price ratio. That's our standard result. And then you end up with the intercept being C over P1 of this equation. And then, of course, F2 is the sort of variable, the choice variable. And so the normal way to do this is just to start drawing in cost lines that have the right price ratio. Negative P2 over P1 is the slope of the ISO cost line. So you draw one here at C3, draw one here at C2, you draw one here at C1, and I'm replacing the number of primes, or the number of apostrophes, I guess, is C1, C2, C3. And if we assume that C prime is less than C double prime and less than C triple prime, then our goal is to get to the lowest cost but still be feasible. Okay, what is the lowest cost combination given the price ratios, right? The price ratio is embodied in the slope of these ISO cost lines. So we're trying to find the lowest cost line that still meets all of our targets. And it turns out you can just follow it down and you'll see it hits that corner right there. Okay, so whatever this is, F2 star and F1 star on this corner that's determined by the protein and the calories constraint, that is going to be the best solution because it gives us the lowest cost and meets all of our targets, right? It meets all of the targets for protein, calories, and carbohydrates. Either it meets them exactly in the case of protein and calories, or it exceeds them. If you remember, this carbohydrate line continues just like this, and so this corner right here, or this kink in this line, is above the carbohydrate constraint. Okay, so that's a solution in two goods. For our lab, we're going to expand and we're going to think about more nutrition targets and more foods. And we're going to do the same exact type of model, though, in a spreadsheet. So I'm going to have you pick 15 foods. You're going to have the prices and the nutrition information per serving for 5 different nutrition targets. And those are all going to be the minimums. And the way it's going to be set up is, if you'll look in the spreadsheet that accompanies this lab, the first sheet is called class data. And I think it has 200 or some different foods. And for each of these foods, you'll see that there's this long name written out to just kind of describe what the package description was, or the food item. So this is a ham and cheddar Hot Pocket, McDonald's Big Mac, Wendy's, Dave's Double, whatever. So there's all of these foods, and then there's an abbreviation here. Then those came from, I guess, the class that collected these in Wisconsin. So the students had to put some identifier here so that they could track which foods they entered into, because this is a class-wide database, so the entire class collected this. And then we have these columns here. So I said we would get the price. This is a per serving price, hopefully. And so if you came down here to the Wendy's, or let's go to the Arby's roast beef, yeah. So it's $3.29 for a sandwich. It says that sandwich is only 350 calories. I don't know. We're going to take the data as true, but I've had a classic roast beef. I'm guessing it could be a little stronger than that. So it's possible that some of these data are off. These are undergrad students just like you that collected this. But anyway, we're going to take it as true. So it cost $3.29. It gave us 350 calories, 12 grams of fat, 39 grams of carb, 2 grams of fiber, and 23 grams of protein. Okay? So if we track this all the way across, that's one of our food choices. If we pick this and put it in our model, that's one of the food choices that we would subject to our model and see if it is a low-cost source of calories or protein or carbs or whatever, and is it useful in meeting our targets. Compare it to something like Kraft macaroni and cheese up here, 60 cents per serving, 250 calories for 60 cents. That's a very, compared to the Arby's classic roast beef, that's very cheap calories. 3 grams of fat, 47 grams of carbs. Again, right? The cost here is 40 cents. 60 cents versus 329. So you can start to see how the analysis is going to work. But where does it suffer? Well, it's only 9 grams of protein. Arby's roast beef is 23, so it's 2.5 times. But the cost is 2.5 times or more. So these are all the kind of things that you would do, and you can see how long and how many multiplications, right, you'd have to do here to compare just Kraft mac and cheese versus Arby's classic roast beef and try to do the economic analysis. Well, we would probably find that Kraft mac and cheese dominates in terms of all of these, except maybe fat, right? So there's 4 times as much fat. Well, even then, right? So it's 4 times the cost. So what are the cost-efficient sources, right? So almost all food away from home is going to be an expensive way to get certain things in your diet. Okay, and so this is the way the data is set up. And then I just want to, so here's this, you read down the column and you'll find for any food, the calories, the fat, the carbs, whatever. But there's this column here that's left in as a blank, and it's an important column. It's a way to structure this so that we can actually set this model up quite quickly. And so when you are selecting foods out of here, you're going to select the entire row all the way from long name over to protein and leave that blank in, and then you'll paste those in. And I'll work with you, show you that in a minute. And then, so the second sheet after class data is your data, and that's where you're going to pick and you're going to fill in an entire row. You're going to paste it in, food 1, 2, 3, all the way down to 15 foods, okay? So you can just copy directly this row. You cannot use a formula, okay? So you have to cut and paste these. You can't put a formula or links to the other page, I don't think. Just don't try it. Just cut and paste this row from long name over here and then make them match up. And so what's going to happen then is you'll end up with, I have here 15 foods that can be compared in these terms, but I'm not going to sit there and try to do my comparison. I'm actually going to set up what we just talked about. I want to measure the total cost, and I am going to measure my total demand or my target in my diet for calories, fat, carbohydrates, fiber, and protein right here. Okay, and so we end up with this. When you open up the class spreadsheet, this part right here will be blank, this right-hand side row. And that's where you'll go and fill in nutrition information of yours. So I've set the calorie minimum at 2,200, the fat minimum at 20, the carb minimum at 130, the fiber minimum at 31, and the protein minimum at 56. These are the targets I have to hit. And then the spreadsheet itself is going to have some formulas right here for you to fill in. Formulas right here for you to leave alone, and the problem will work itself out for you. There'll also be a problem here for the total cost that you can leave that alone as well. This row is not to be touched. This row, you're actually asked to enter in your own information. Okay, so now I want to walk you through the spreadsheet just a little bit. So again, I'm on the Your Data spreadsheet, and I've already copied in, so in these columns, I've already copied in my 15 foods, copied the entire row over to here, and then I told you there were going to be formulas already entered for you, and so let's start right here with the total cost. So this formula is already in the spreadsheet, it's supposed to be there. And if we highlight it here, you can see that, or you can look up here, whichever is, I guess they're the same size. It uses the sum product formula. So D3 to D17 is this blue column, and then E3 to E17 is this red column. And so what the sum product formula does is it multiplies 35 cents times whatever value is here, and then it adds to that 43 cents times this number, then adds to that 89 cents times this number. So it's a quick way to multiply two things and then add up the entire column. Okay, so you obviously could do that by making a new column, but this just shortcuts it. So it's 35 times 0 plus 43 times 0 plus 89 times 0. So if you started putting numbers in there, you would see those fill in. And so let me just show you how that looks. So if we added one of these and then two of these, you would see that you're getting 43 times 2 is 86 plus 35 is $1.21. And so this is the cost. This cell right here is tracking the costs of your diet. Every time the choice variable column, which is that blank that you left there, every time these adjust, the cost will adjust. The other thing that happens when you put in new values here, 1 and 2, is this left-hand side over here starts changing. So now we're up to 500 calories, 21 fat grams, 74 carbs, 5 grams of fiber, and 6 grams of protein. Okay, and so when these things changed, the formulas that I already given you here started adjusting as well. And so let's look at those formulas. And it's the same kind of formula. It's E3 to E17, the choices, multiplied by F3 to F17, this red column. Okay, so what's going on? 1 times 200 plus 2 times 150 plus 0 times 150. So this is just an accounting of every time we make an adjustment to the food choices here, this is making accounting of what are the total calories in the current setup, what are the number of fat grams in the current setup. Okay, and so it's just an accounting model right now. We have to do a couple things. And if you look at this area right here, it says left-hand side sine right-hand side. Okay, and so if you think about it, it's top to bottom, I know, but if you think about it in equation terms, there's a left-hand side of an equation or an inequality and the right-hand side of an inequality. And so think about it in that way, and then the left-hand side is how many calories have we accumulated, and it must be greater than or equal to whatever I stick on the right-hand side. Okay, 21 here must be greater than or equal to whatever my target value on the right-hand side is going to be. Okay, and so the last thing to do then is to fill in this right-hand side. Actually, I'm going to go ahead and zero these back out. So there's nothing going on in the calculations. Those formulas I'm going to leave alone. If you look here, it says enter your data from the class data sheet up here, in between here, and the food 1 to food 15 is listed there to guide you. Then it says don't change anything in this row. It has the formulas you need, so this row should be untouched. But here it says use the diet recommendations to identify target levels for relevant age, gender combination you want to analyze. And so when you look at the handout for this lab, it has a link to the famous 2015 USDA Healthy Government guidelines, diet guidelines that we talked about a little bit. And so if you go to Appendix 7 of that document at that link, you'll find a big long table that you can scroll from right to left through and find what you want. And I went to, because I am in this group, male 31 to 50, and I'll use that to fill in my right hand side values. So 2,200 calories is going to be the minimum. For fat it says 20 to 35. Let's just go with 20. You make whatever choices you want. For carbs it said 130 grams. For protein it said 56 grams. For fiber it said 30.8. I'm just going to put 31. And then for protein it said 56 grams. Okay, so I've now got something that I could start to play with. All right, I could start adding things in, foods in, and see, how things build up towards meeting my requirements and what the cost is. But this is an optimization problem, right? We already went through the graphical solution and said find the lowest ISO cost line. Well, we can't do it graphically, but we can use Solver. Okay, and so I'm going to take you through the steps here to use Solver, and we'll get our solutions that way. So let's, the Solver tool is in Data up here, and if you go all the way to the right, you'll find Solver. Click on it, and I already have loaded in the what. I'm not sure why the screen black there, but I've already loaded in this stuff, the relevant information for you. As long as you don't change where anything goes, this should work. So D19 is the target variable, or the objective variable, right? Total cost. That total cost, remember, adjusts as we change the numbers in these cells. This cell right here is tells you what you're trying to do. So are you trying to make large or small the objective? And in this case, we're trying to minimize it. And then by changing variable cells, that's just the choice variables, okay? And so that's set for E3 to E17. So as long as you pasted everything in the right row, this thing is already ready to capture those. And then right here it says for the constraints. So take the left-hand side, which are F19 through J19, and make those greater than or equal to F21 to J21, the right-hand side. If for some reason that this stuff wasn't there, right, you just go through and click on the red buttons and make them wherever your total cost is calculated, wherever the changing cells, the choice variables are. And then in this case, I'll delete it and put it back so you can see how to do it. Whoa. Yeah. So subject to the constraints, you would just click on Add. And then for cell reference, since they all have the same middle point, the same middle sign for the inequality, we can right-click all of F19 through J19. And then here we would set that to greater than or equal to. And then for the constraint, right-hand side, you just select all 5 of those. Click OK. I've already got make unconstrained variables non-negative. That means you can't have a negative contribution. You can't consume a negative amount of anything. And then simplex LP is our method, and we click on solve. Okay. So this says solver found a solution, constraints and optimality conditions are satisfied. There's some reports. I'm not going to open those. You can just click on OK, and it will lock in your solution. So what is my solution? Well, it says I can get 2,200 calories, 56 grams of protein, right? So I'm right at my target of 2 things. I'm over the fiber target, over the carbs target, over the fats target. I will be consuming almost 5 servings of Kraft macaroni and cheese, 3.5 great value Smile fruit snacks, and that's what I get to eat. But I can also meet all of my requirements, these 5 requirements, for about $2. Okay, so these are daily requirements. I could be eating for $2 a day, and I trust me, I'm not, and I never would. But this is a useful measure, right? So that maybe it's a starting point. It's a starting point for us to start to think about, one, should we come back here, is 80 grams of fat too much? Well, if it is, then we set another boundary that says, let's go above 20, but not above 45 or above 35. And that will cause this problem to change. It will cause the cost to go up because I'm saying now that I want a boundary between the two. Same thing for carbs. Is this thing too carb heavy? Do you have to find a better way of getting the foods? And that would cause more foods to enter this solution but still meet the requirement. So it'll cause more choices to be used. It'll cause the cost to go up, but it'll do a better job of meeting whatever additional policy targets I might have. So we're taking a very simple approach in this lab, so I want you to keep that in mind. Just meeting the targets is probably not enough, right? To get to a true cost of sort of a balanced diet, you would have to start thinking about what are the lower and upper bounds, and then you also would probably have to start thinking about, could someone actually function if they only split their food consumption between some Kraft mac and cheese and then a fruit snack? I mean, that would be repetitive. And so those are the kind of things you're going to think about as you do this. I really want us to go through the practice of solving one of these, and then you'll see from the Lab 4, here's the handout so that you can see all the different definitions of things. But the second page of that handout is here. I've got this in split screen. Is your submission requirements. So we're going to do these. I want these in class next Wednesday, and we're going to talk about them. I'm going to ask questions and do some discussion. But what do you need to be prepared with? You need to tell us what your assumptions were, right? Including what the target level for these things are. And by target level, I mean that minimum. We need to know what the minimum cost of your target diet or the solution diet was, right, from the spreadsheet. And then just like when I said protein and calories were the ones that the targets that I just met, you're going to tell us which nutrition factors were limiting in making that low cost. And then I want you to bring a couple of short answers, so 2 to 3 sentences. How would you expect the minimum cost estimate to change if you doubled the number of foods? Instead of 15 foods in your model, you put 30. And then think about, what if you used every one of those, 250 different food options? And then the second thing, what if you expect the minimum cost to change if you added constraints on servings across food groups? So instead of saying five servings of macaroni and cheese per day, no food is going to be consumed more than 2 times, right? So no more than 2 servings of any one food. How do you expect those to cause changes? And you can play with those and try to model those things if you want, but we are going to spend a little time talking about it on Wednesday, and I can walk you through it. But I want you to think it through just from what you understand from the graphical sort of analysis we did today. With that, I'm going to let this thing start rendering and put together your basic spreadsheet model for you so that you can hopefully get through this without too much trouble. That'll close out our Lab 4 presentation.